Now, our session with engineer Josh Black, and this topic about material selection in material field. So, engineer Josh, can you hear and can you present now?
Yeah, for sure. You guys able to see me okay?
Yes.
Awesome. Okay. I'm gonna share my screen. Um, Perfect. Can everyone see that?
Yes, it's clear. Yeah,
Perfect.
it's
Okay.
true.
Awesome. So, hey everyone, I'm Josh. I'd like to start off by saying I'm actually an undergrad student in materials engineering, so I don't have my eng just quite yet. I'm in my third or fourth year of my undergraduate studies at McMaster University out in Canada. I'm very excited to be here today, and I just like to thank everyone for organizing this amazing event. It's just really exciting to see a bunch of students getting together and supporting each other under these, studies. So I'm going to be talking a little bit about material selection, going over a bit of an agenda for what I'm going to be talking about this morning. We're going to be going over material selection, what it is in general. We're going to be doing an overview about everything in terms of material selection. We're going to be talking about material performance indices. I'm going to be introducing you to a software that I use called Granta. It's a very good software if you want to go into material selection. I'm sure if you get a job in material selection, you'd also be using this software. We're going to be doing a little bit of a demo using Granta. I'm going to show you some cool things you can do with it. We're going to be talking about a bit about machine learning material science, just the really brief overview about it. I'm going to be talking about some projects that I've done in that, and then integrating material science into material selection. And then I'm going to have some time for you guys to ask some questions at the end. So before we jump into the demo, what is material selection? So we know that in any materials or any engineering application, we're going to have a physical model. Now you can have these ideas, however, in order to actually create a product or create a solution to these engineering problems, we need to have a physical model that is made out of any specific materials. And that's where we as materials engineers come in. So engineering problems have these functions, objectives, constraints, and different free variables. Our job is to manipulate certain equations that incorporate all of these variables and constraints, functions, and all that. Our goal is to manipulate these equations to create a ratio of material properties that we can then optimize under material performance indices. So what's a material performance index? Essentially what it is as I mentioned before, during a material selection process, we are given different materials or different equations to manipulate. From there, our goal in that is to end up with an equation that has a ratio, some kind of ratio of two or even two or more material properties. So as you can see on the chart that I have up here, we have density versus elastic modulus, and we ended up with the MPI that had a ratio between elastic modulus and density. And again, up here, another elastic modulus density ratio. Our goal then is to, depending on our problem, minimize or maximize this ratio in order to have a good material for the problem at hand. And this problem here was plotted on what we call an Ashby chart. We're going to be using these Ashby charts a lot in today's session, and these Ashby charts are really good in material selection based problems because, as you can see, they're allowing us to plot a bunch of families of different materials. We have all of our polymers, all of our metals, ceramics, and whatnot. So it allows us to plot different types of materials against each other, and using our knowledge of each material, kind of choosing the optimal ratio, which is going to be somewhere up here for this case in the upper right hand corner. So now, just before going into our demo, I'm going to talk a little bit about Granta EduPack. It's an ANSYS software. I'm not sure if your school has this, but here at Mac we have a license with ANSYS. So in our first year of engineering, we get this software that we get to use all the way out through fourth year. There's also a couple cool classes that go into Granta or go into ANSYS. and their finite element applications. But today we're just going to be focusing on Granta. It's a material selection software used to compare and contrast different materials. Essentially, it's a huge database of a bunch of materials that has a lot of different material properties. So you can compare and contrast different materials against each other in your material selection process. So let's go into a little bit of a demo of material selection. This is actually a project that I did in my first year. It was a wind turbine blade material selection. So we were given a specific scenario to create a wind turbine blade for a client. So this was a completely hypothetical topic, but the gist of the problem was we're to design a wind turbine blade using a material with a minimized mass. So all groups were asked to minimize the mass, but depending on your scenario, you would want to have a maximum something else. So in our case, we wanted to maximize the yield strength of the wind turbine blade. We were given a bunch of equations to work with. So we were given the equation for the deflection of the wind turbine blade, the moment of inertia, the area of the wind turbine blade. Now, these are just a bunch of geometric parameters. It was like an ellipsoid, which is why we have this A plus B in the area term. We are given, obviously, the stress, but I think this is pretty self-explanatory. And then we were also given the mass because we wanted to minimize the mass. So from here, your goal is to manipulate these equations. What essentially you want to do is you want to find what your free variable is. This is the variable that can that you can change in your material selection. So something that isn't totally constrained, something that is free to change. So we wanted to then relate our yield strength back to our mass. So identifying that free variable would allow us to link our yield strength to our mass. And this ended up being the thickness. So we have in this first equation here, our yield strength has to be greater than or equal to the force divided by area. And we can see that this T term is in the denominator. And if we go into the mass term, we also have this T term in the numerator. So essentially what we then did was rearrange our equations for that T term. So we had our T has to be greater than now force divided by a part of our area term multiplied by our yield strength. From there, we could plug that T back into our mass equation. And then we were left with this equation here. The pi A plus B kind of canceled out. And we are given this constraint here. Our L, the length of our turbine blade, would be our constraint for our geometry. The force is our physical constraint. And then this ratio here, our density divided by yield strength, that is the inverse, actually, of our MPI ratio. So this is the ratio that we want to work with in order to minimize mass. So from there, in order to find the ratio that has, the minimum mass, we will then have to maximize what we call their MPI ratio. And as mentioned previously, our MPI ratio is the inverse of the ratio that minimizes mass. So we want to maximize this MPI ratio here, our yield strength divided by density. Maximizing this would minimize our mass. So from there on all Ashby charts, they use a log scale on the X and the Y axes. So if we wanted to make this a linear term, we would then take the log of both sides, rearrange, and now we are able to, plot this as a log chart. So we have the log of the yield strength on the left-hand side, the log of the density on the right-hand side, along with the log of the MPI. From there, I hopped into Granta and I made a Ashby chart. And then we have this Ashby chart show up here with the density on the x-axis and the yield strength on the y-axis. Now, all of these bubbles here are just a bunch of families of materials. And I'm actually going to hop into Granta right now and show you guys how I made these charts and show you guys a few tricks that you can use in Granta. Perfect. Can everyone see this screen? Mohammed, can you see this screen here?
Yes, I can see.
Perfect. Okay. Awesome. Yeah. So this is the Granta interface. I'm not sure if anyone's used it before, but I'll do a quick overview. So this is what you get when you first log into Granza, the first thing you see. Before we get into creating the charts, I'm currently on what we call the level 1 database. So this is a very simplistic database. If I go into my materials, you can see that in the level 1 database, we have a very low level amount of material. So I'm going to click on my metals and alloys. I have a ferrous versus non-ferrous category, but it's not too extensive. So it's good to get just a high overview of what we might want when selecting materials. We have low carbon steel, medium carbon steel. What does that really mean? Well, it'll give us an idea of the types, the grades of steels, if we happen to land on it, the grades of steels that we might want to use. From there, we'd be able to, use our own judgment using different heat treatments and whatnot, different grades of steel to make our final decision. Now, if I change my database level and I go to level 3, the more advanced database, now you can see if I go on to metals and alloys, go to ferrous, I have a lot more options. So if I want to now look at carbon steels, low carbon steel, I have a bunch of options when it comes to cast and wrought steels, depending on their heat treatment as well. Now, it's not an extensive heat treatment list, but it'll do for a high level overview of what's happening. So I'm going to go back to the level 1 database, and as you can see, there's also polymers, elastomers, different types of polymers. So it gives a wide range, and it just gives you an overall look at your grand scope of what's going on for your material selection, which is good for your initial analysis before you dive into anything too technical. From here, if I go to this chart select, I'm now going to create that same ASHV chart that we saw before. I'm going to click on chart index, and we said our y-axis was going to be a yield strength, and we said our x-axis was going to be density. From there, I'm going to click on these bubbles at the top, and we have our ASHV chart. Now, the one last thing that we need to do is we need to actually place our index on it. So we had a slope of 1. From there, depending on what the line goes through, it'll either gray it out or it'll have the line going through, it'll have some nice color in it, showing that, hey, we actually can select this material. So the higher the MPI is, we saw that was the y-axis in that, the y-intercept in that linear equation there. The higher that MPI is, the better the ratio we're going to have. So right now, it's looking like for that problem there, some steels would be a good choice of wind turbine blade, which obviously it does work because that is what wind turbine blades are made of. We have nickel alloy here. And then down here we had tungsten. Probably wouldn't use tungsten because it's super heavy. So now moving on, what's really cool about Granza is, let's say we wanted to compare something else. Let's say we wanted to now, instead of doing yield strength versus density, I wanted to compare Young's modulus versus density. So now I'm creating a new chart. So this is the chart explaining Young's modulus versus density. And it carries over everything that I've selected or not selected in the initial graph. So if I also have a slope of 1 on this material selection, you can see that now that I've, kind of said, okay, I don't want these materials, it's underneath my line, it's not going to work for my application. If I go back to stage 1, those same materials are grayed out because it knows I don't want to use them. I can do the same thing if I bring this line up a little bit higher, go over to stage 2, it grays out, a bunch of different materials. And that's really good for application if you want to compare 2 different scenarios. Let's say one, I wanted to compare the strength, which was my yield strength. And then I also wanted to compare, say, the deflection of my wind turbine blade, which is why I might go into Young's modulus. It's good that I can compare the 2 at the same time. What I think is really cool, though, is if I go back and I wanted to put a constraint on the price of my material. Let's say I did really care about my yield strength versus density ratio, but I also wanted to have a relatively cheap wind turbine blade. Now, if I make a chart and I now plot again yield strength, and I'm going to plot it against price here. And this gives us price per kilo of each material. I have this Ashby chart up here, and just like before, I can plot a slope. Okay, but then I'm kind of clicking back and forth. What if I want to compare them directly to each other? Well, that's completely fine, because what we can do instead is have our yield strength be on the y-axis, and then our x-axis, we can have it more advanced x-axis. And now what we can do is we can plot density multiplied by price, kind of seeing what that interaction between the two of them is there. So now this new chart plots your density and your price on the x-axis, and then it plots your yield strength on the y-axis. And then from there, it's kind of the same story, but I'm now getting a whole different Ashby chart compared to my first one up here, and then my price one that I had go away. So depending on what you're looking at, if you're just looking at your yield strength versus your density, you might want to move this all the way up here and say maybe, okay, some kind of steel is probably my best bet. From there, you can go into all the different treatments of steel and whatnot, and it would give you a better idea of what material to select. So I'm going to go back into my PowerPoint. And now we're going to talk a little bit about machine learning in material science, which is a really big topic as of late. I know a lot of people more and more want to get into machine learning and kind of merge that bridge between software and materials. And it's a growing industry, and it's something that has a lot of attention towards it right now. I personally think machine learning and AI is the way of the future. Is how we're going to, in the future, make different heat treatments. It's how we're going to end up selecting materials. It's how we're going to predict material properties. And I'm just going to give you guys an overview about what's going on, my thoughts, and how we can integrate it into material science and engineering. So machine learning and material science, what is machine learning? If you don't know, essentially what it is it's a tool used for prediction. So I know we have a lot of generative AI right now. What that is doing is it's taking your inputs that you're giving it, and it's predicting what you want the output to be based off of a bunch of iterative regression models. Now, these are more complex regression models, but what they're doing is they're taking that input, and based on what you've trained your machine learning algorithm on prior, it'll take your input and it's going to give you the predicted output. Now, this can be used for a multitude of applications in the material science world, including kinetic modeling, prediction of microstructural evolutions, simplification of systems using principal component analysis, which we're not going to get into today's talk, but there's a lot of research on PCA. That's really cool. And development of material properties, mostly through microstructural evolution as of right now. Going up to this image here, it just gives you a wide variety of what's currently being researched in the machine learning world of material science. So you have model development. This is, simulations of how different material properties changes. You have generative design of different microstructures. You have adaptive design here. Molecular and atomistic simulations, which are pretty cool. We can kind of see what's going on the molecular level, materials characterization, and a whole bunch of other awesome applications. So whenever I talk about machine learning, I'm not sure how everybody's machine learning knowledge is, but in very simple terms, instead of when I normally code, if I'm normally coding something, I want an input, I'm going to code the rules, and then I want a specific output. For machine learning, I'm going to give my algorithm an input, I'm going to give my algorithm an output, and then based off of that, the algorithm is going to make its own rules to be able to predict what's going to be going on. So just a large overview. This is just a very broad overview of what's going on in machine learnings. So a lot of machine learning applications, especially the ones that I've worked with, use something called gradient descent. And gradient descent, essentially what it is it's a complex regression model that iterates upon itself a bunch of times. So what you're going to do in a machine learning model is you're going to have what's called a training and a testing data set. Initially, when we're first making our machine learning model, we're going to use our training data set to create this regression model. Now, my training data set has inputs and it has a bunch of outputs. I'll talk about what mine was in my project. So for my project, I made a machine learning algorithm that was able to predict different fractures based off the pictures. So all of my inputs were the pictures of the fractures, and all of my outputs were the corresponding fracture modes. So what it did based on this is it took the inputs and it made a bunch of rules based off the inputs. Essentially, what it did is it counted each pixel and it was able to find out what different collections of pixels would look like. From there, having all those inputs and outputs, the algorithm would try to link those inputs and outputs together using this regression model. And the goal of any regression model using gradient descent is to minimize the mean squared error, and it kind of does a linear system of all your inputs. So this is just a simplification of a system. So if we had a just a linear system here, we wanted to model it as A1 times X. So A1 is your slope, and then A0 is going to be your y-intercept. It models this against your actual y value. So it models your the x that you're predicting against the y value. From there, it takes the mean of all of your inputs, all of its squared error values. So this is the squared error. It divides it by everything. So it sums up all of your squared errors, then it divides it by how many inputs you have. So it takes the mean squared error. And you want to minimize this. We want to have the smallest squared error as humanly possible. So to do this, we're going to be using gradient descent. Essentially what it does is I'm going to take both of my parameters, my A1 and my A0. I am going to then try to find their optimal value, because those are the ones that are not changing. They have to be constant throughout my entire machine learning algorithm. My X and my Y are going to change, but I need to find the correct combination of weights or A values in order to have a working model. So I'm going to take their derivatives, and I then end up with these equations here. My A is going to end up converging at some value, but I'm going to do this by iterating over the A naught values that I find, so my initial A naught value, and I'm going to subtract the derivative that I took right here, multiplying it by some value gamma, which is the learning rate. So the learning rate is how fast or how slow my machine learning algorithm is going to learn, and depending on that learning rate, your algorithm might succeed and it might fail. Now, after I find the correct combination of A values and A naught values, I'm going to then test my machine learning algorithm. So this is where that testing data set comes in. So we trained it, we got these correct weight values, these A values from training it and using that regression model. Now we're going to test it under a different set of inputs and outputs. This input and output set, my machine learning algorithm has not seen at all. That way we know that since it hasn't actually been trained on this set of data, we can tell that it's going to have some outputs that are going to reflect what it would look like if it would see a brand new piece of data. So now that I give you kind of the gist of how machine learning works, this is a very crude overview of how it works. I'm going to talk about something that I worked on last term in my machine learning class, which I mentioned previously very briefly, was my characterization algorithm on how to characterize different fractures in SEM images. So what me and my partner did is we took a bunch of SEM images of fatigue failure up here, ductile failure down here, and then two types of brittle fractures. We kind of link these two together to just make one brittle fracture group. So there were three different groups you could characterize our fractures in: brittle, ductile, and fatigue-based fractures. They're very different. And what we did is we made a machine learning algorithm out of a convolutional neural network, a CNN. Maybe you've heard of that, maybe you've not. But essentially what we did is we used this CNN to make our machine learning algorithm be able to predict what kind of fracture was being inputted into it. And the thing about these fractures is these are very telltale. Okay, we can tell just by looking at it that we have fatigue, ductile, and brittle fracture based off of them. The thing about this is some fractures have mixed fracture modes. So you might have a fracture that has some ductile and brittle fractures. And a materials engineer might not pick up on this in a forensic analysis. So using this machine learning tool, you can kind of see if your hypothesis is correct. Now, this machine learning algorithm had around an 88% accuracy, but that's because we also inputted some mixed fracture modes. So it might have been picking up on something that we maybe had incorrectly labeled or was in the wrong section. But that's exactly what its job is to do. Is to obviously correctly segment each fracture, but B, it's able to fact check you. Maybe I thought that this fracture was brittle, but it ended up being a fatigue-based fracture based off of some beach lines that you see here, some striations. And if we look at that picture again after inserting into the algorithm, now I see these beach lines. It was a very interesting project to work on. It was a very intense one, but it's something that was very interesting for me to learn. And now that I've developed that, I personally feel like developing another algorithm for very, very different images would be so much easier, because some of these images can be the same, and that's where our issues laid. So now, how can we link machine learning to material selection? Well, as I mentioned before, machine learning is all about prediction. And if we can use machine learning as a tool to predict how something is going to evolve in say a microstructure evolution in this bottom picture here, like casting, if I am able to predict how that microstructure is going to evolve, if I'm to cast it, then I can try and see, okay, what can I fix? What can I change about the simulation to make, smaller grain sizes, to make less dendrites, to make more equal sized grains. So microstructure evolution is a big one in machine learning, because I can learn how I can predict different changes in phases or different solidification techniques. So using machine learning, it's essentially what it's going to do is it's going to allow us to more accurately manufacture different materials, taking out defects and ending up with the optimal material properties that I can then use in my material selection. With that, that's all that I prepared for you guys today. Thanks so much for having me, and I'm going to go back here and I'm going to open up the floor for any questions.
Anyone have a question can raise your hand, and mic is on. So you have the ability. I see no one has a question, so I get my one. So how to start this journey of integrating AI, machine learning within the material field, the roadmap.
So how did I start? Was that your question? If I
want to take the career of integrating material and AI, what the roadmap should I take? How to start the stages and final destination? How can I see this in progress?
Yeah, for sure. So I'm in that role as well, right? Like as I said, I'm in my third year, so I'm currently looking for opportunities in that industry. But what I'd say is I would try my best to get an internship somewhere that would have some kind of material selection component to it, and then make your own project that says, hey, like I think I could use some machine learning skills to model something for you, just like how I did in that project that I did in the fall. Hey, I think we have a lot of different fractures coming in, and we have to go into the lab a lot, and sometimes we might have different differing opinions on these fractures. So maybe instead I can make a machine learning algorithm that would suit this. And in my personal opinion, if you come up with a project in a internship, a lot of the times you're going to be given that green light on it, because as an intern, you are, in my personal opinion, you are, getting replaced a lot. And if you can even make a little bit of a change in the company, if you can make a little bit of an improvement, that's going to raise your stock. I had a 4-month internship with a company, and I did a small project that helped improve their economics. And because of that, small project that I did in like 2 months, it was like a 2-month project. It essentially it made me more marketable, and they brought me back for another internship, and I'm going back with them for a year now. So if you can make a small project that shows that you're invested in it, and you can link different parts of the material industry to machine learning, if you can link it together, then it'll jumpstart your career, and then you can add that to your resume. You can go in and apply for larger companies. I know companies like Tesla, they do a lot of machine learning and material science. They're a big material science company. So if you're able to get a job with them, you can really quickly make that link. Anyone else?
I think that's all, Josh.
Yeah,
Thanks.
no
Thanks for
problem.
the invitation. Thanks for the presentation. We hope to meet you in the future. And
For sure.
thank you.
Yeah. Thanks so much. Thank you for having me. This is an awesome event. I'm so glad that I could be a part of it. Yeah, thanks so much.